Hello? Hello? Okay. Well, we're about to get started. So, hello everybody. My name is Nicholas Matsakis, and I'm working on Rust. And I want to talk to you about today, kind of give an overview today of how it works and some of the things that are unique about it. So, the first thing I wanted to answer is a question that I think everybody has on their minds, which is, do we really need another programming language? What is Rust bringing to the table that other languages don't? And I think the answer has to do with this trade-off that you find in most languages. So most languages are basically trading between control and safety. You have something like C++ that gives you a lot of control about what the machine is going to do at any point in time, but you get almost no safety guarantees. It's very easy to crash or to have undefined behavior and things like that. In contrast, you have something like Haskell. You define your program in a very abstract way. It's very good safety guarantees, but it's really up to the runtime to figure out how to execute it and to make it efficient. And if that works for you, great, but if not, you have a problem. And then in the middle, you have languages that have different amounts of runtime. So something like Java or ML, they give certain safety guarantees. Maybe they won't have dangling pointers and so forth, but they have also a certain amount of control, but not as much as C++. And what we'd like to do with Rust is to kind of step off this line and say, we can have control and we can have safety. We don't have to give up on either one of them. And the reason that this is particularly interesting to Mozilla, I think maybe it's probably clearer to this audience than other ones I sometimes am talking to, but is browsers really need both of those things, right? Sometimes you need to have a high-performance part of your browser where you need a lot of control, and we care a lot about memory consumption across tabs and things like that we want to be able to track and take control of. But other times, we really just don't want, well, we're also going to random web pages and running random code, and the world is trying to hack into our browsers all the time, so we need to have some measure of safety, right? And we're working to validate. Basically, Rust is designed to be a good language for building browsers in. And as part of that, we're validating it with a Servo project that you may have heard of, where we're trying to re-engineer Gecko and some of the core parts to work in a more parallel, more future-proof way. But let me get a little more specific and give you some examples about what I mean by control. So this is a little C++ code here. And it's just 3 lines of code, but it's already got a lot of features that most languages don't have. Right? So you start off on the first line, you have this vector of strings. This demonstrates something which is basically stack and inline layout. So in C++, when you put a vector variable like this on the stack, what will happen is that the fields of the vector are inline directly into the stack. So you can see in the diagram we have the data and the length of the vector and the capacity right there in the stack directly, rather than a layer of indirection. And then when you go into the stack itself, you'll find that the entries in the stack, they're strings, and they're embedded directly into the array. So that means if we look in there, every string is itself kind of a vector of characters. There will be those 3 fields laid out in the array, the data and the length and the capacity. Right? And there's no indirections there either. So you have just 2 hops to get from the vector to the character data. And then on the next line, we have this little lightweight reference. And that basically is a pointer directly into the middle of a vector. So that's really useful when you have inline layout, because you might have, say, a string that's kind of big, and if you had to copy the value out of the vector into your stack or something like that, that would be expensive. So you just want to make a pointer right into the inside. And then finally, there's no code here on this last line, but there is something that takes place. When you exit out of the example routine, the destructor for the vector is going to run, and it's going to free the memory automatically right there, deterministically. So that's particularly useful if you want to control your maximum memory usage and things like that, to know exactly when memory is going to get freed. But take a little bit more broadly, I would say, what C++ is giving us through features like this is essentially the ability to define new abstractions, like a vector even, that optimize away to essentially nothing. So if you wrote some hardcore assembly code or some C code, it would basically run in about the same performance as some nice vector code, nice C++ code that uses vectors and looks much nicer and higher level. And that is something that a lot of languages compromise on. So, for example, this is the memory layout, roughly speaking, of a vector in Java. You see there's a lot more boxes here and a lot more layers of indirection. If I want to get from my vector to my character data, I've got to go through 4 pointers. And if I'm going to add new levels on here, maybe some water bottle. Might want to fix that. If I'm going to add new levels,
sorry.
it's okay.
Oh, someone else in common joined the room.
It looks very tasty. It's making me thirsty, but other than that, I know. And I got nothing. Well, memory leaks, I guess we can go with that.
Sorry, the video admin from Mountain View joined, and for some reason,
You see in this little box here, is that enough? Yeah. So as you add more water bottles, Okay,
sorry.
there we go. Right, so what I was trying to say was you have a lot of layers of indirection, and this only gets worse as you add more data structures on top, right? So if we have an iterator over the vector, that's going to be some more objects, and if we have a hash map that's built on top of a vector, that's just going to add more objects into the picture. And it's not just memory layout, it's other things too, like guaranteeing static dispatch, C++ style template expansion, so that if you have some code that you make a generic function for, you're going to make a specialized version to every set of argument types so that it can be optimized very well. All these things add up, and that's why C++ basically runs really fast in a lot of situations. On the other hand, all these advantages, they come at a price, right? C++ gives you a lot of control, and so much control that you can shoot yourself in the foot extremely easily. So if we go back to our example, we have this reference pointing into the vector, and then we might have the next line, which is going to append some data to the vector. And that looks innocent enough. But what can actually happen here is that when you add data to the vector, if the vector is already at its capacity, we're going to allocate some new memory, copy the values over, and then free the old memory and redirect the pointer. And now the vector is fixed up. The vector is fine. But this extra reference, this element, is just hanging out. Right? And that's called a dangling pointer. It's pointing into freed memory, what used to be the vector, but now it's nothing. And that is going to be a problem if you try to use the pointer, like print out its contents or do anything with it. So what happened here? What went wrong? And I think the bottom line, the fundamental ingredients of what was happening is we had aliasing happening. And by aliasing, I mean you had two pointers pointing at the same memory. In this case, we had the original data pointer, and we had the reference. And then we had some mutation, which is to say we pushed a new element on the vector, and that caused us to free the old contents, right? And the vector was easily able to patch up its own pointer. It patched up its data pointer to point at the new contents, but it doesn't know about all the other aliases that exist elsewhere in the system, so they're just incorrect. So I'm going to come back to this theme a couple times in my talk, but essentially a lot of these memory problems that we're really interested in solving come down to these ingredients: aliasing and mutability kind of combined. And so what Rust is partially about is giving you C++ without those ingredients. But let's address one other thing. The traditional answer to dangling pointers is to bring in a garbage collector. Right? That's what pretty much every language other than C++ does, every modern language. And the problem with this is, well, there's a couple problems, I guess. One immediate one is that really compromises control. I mean, a garbage collector, essentially how it works, when you need some memory, it's going to go scour your system to find if there are any pointers, and anything that it's not pointed at, it's going to free it. So you don't really have a lot of input in that process. It'll do it when it wants to, and in a way that however its designers intended it to do it, right? It also requires a runtime. So we would really like Rust to be more like C, sort of act as, you give it a stack and it can execute. That's all it really needs. No, it doesn't place a lot of requirements on its host system. And that, if you have a garbage collector, then that sort of works against that, because you must have some sort of runtime to bring in the garbage collector to make sure it runs and everything else. But the last reason is that I think a garbage collector doesn't really solve the whole problem. And let me explain what I mean by this. I mean, in particular, it doesn't address data races. And it might not seem immediately that data races and memory safety are so related, but I think that they are. So let me show with some abstract box diagrams. So if you imagine that we have some function executing, represented by this square, and it allocates an object, and then it wants to free the object, right? The memory safety problem comes about basically if there is any pointers after you free, if there were any other pointers you didn't know about into that memory, right? So to put it another way, if you want to free an object safely, you have to be sure that there are no references left. Okay, so now let's think about two threads running, and say one of them allocates an object, and it wants to give it to another thread. Okay, now we can have a problem, basically, if there were any references still from the original thread pointing at this object. Because we've given ownership to the new thread. The new thread is going to expect to mutate it and change it and do whatever it wants. And yet the old thread, if it still has any pointers, they might conflict. So basically, we can say that if we want to safely send the object, we have to be sure that there are no remaining references at the time we send it. That might sound, I mean, these sound pretty similar, right? So basically, if I know that I can send the object, I also know that I could free it. So if we have an analysis that proves that we can send things from one thread to another, that same analysis proves we can free the memory. So that's what we hope to employ. Basically, we hope to kill both these birds with one stone. And the way that we're going to do it, well, we're going to look at what people do in practice. Right? So if you're writing C++ code today, the only way you can hope to have a program that doesn't crash is you basically come up with some safe conventions and you follow them as strictly as you can. And modern C++ has already come a long way towards defining a lot of conventions, right? So we have ways to say to your caller, what are you going to do? Like, here's a pointer that I'm only going to read. And then I could use, that's a const reference. I could use an L value reference to say, this is a pointer I'm going to write to. Or an R value reference means I'm going to take all the bits of this object and reuse them. And finally, you can have like a unique pointer that says I'm going to take ownership. Right? And these are really good strategies for sort of coping with C++ code. And it's definitely progress in the right direction, but it doesn't make the language safe. There are still plenty of ways, even if you correctly document all the types and give const correctness and everything else, you can still screw up. You can still have iterator invalidation and double moves and all kinds of ways to get undefined behavior. So what it comes down to is that these mechanisms are sort of unenforced, almost, not documentation, but they're unenforced by the language. Right? You have to follow them yourself. Nobody's making you do it. So what the idea from Rust is, let's take those safe patterns, let's codify them, write them up in a more formal way, and then use the type system to guarantee that you follow it. So if you do this, if you follow rules like all memory has a clear owner, so you know when to free it, and when you're iterating over a vector, you can't change the vector, those kind of rules, then you don't need a runtime to prevent crashes. The rules are going to prevent the crashes for you. So to be fair, these ideas aren't really our own, I think. Rust basically takes ideas from a lot of different languages, like C++, of course, as I've been talking about. Also, I think from Haskell and ML and Cyclone, and some research languages like that. And we're putting them together in our own way to do our own thing. But we owe a lot to those that came before us. And of course, I also want to say that Rust is where it is today only because of the great open source community that has evolved around it, which has been the source of a lot of ideas and also a source of negating a lot of our less good ideas. So we're grateful for that. Now, let's look at these patterns and how we can solve them. Right? So the Rust type system is based on essentially this observation that the dangerous things happen when you have aliasing and mutation at the same time. The problem is, the reason these two things are necessary is because aliasing is what makes dependencies non-obvious. Right? It hides the dependency. That's why like the vector could update its own pointer, but it doesn't know about the other pointers that are hanging out in the system at large. And mutation is what actually makes things change. So if everything is static and you're just reading it, then it's fine. But once you start introducing mutation, things start to get freed and problems can arise. So in Rust, we basically we have three basic patterns that we adopt and use throughout the language. There's ownership, which is basically just T. So if you have some type, you own it. I'll explain this in a second in more detail. Shared references and mutable references. So let's see how they look. So with ownership, you have, this is probably the most basic pattern, I would say. And I like to explain it by referencing objects in the real world. So if you think of yourself, or if you think of a book that you might own at home and it's on your shelf, you already know a lot about that book. Like, you know that nobody else is using that book unless they come and talk to you first, because it's on your shelf, right? And it's the same way with a data structure. If I own it, if I have a vector, I know that nobody else is reading it unless I give it to them, essentially. And just like books and things like that, I can transfer the ownership of this vector to somebody else. So if in that case, I've given it away, and they are the new owner, and I don't matter anymore. I don't have access to the book unless I go through them now, right? And in particular, I could return or terminate in some way, and the book is still in use by the new owner. But if that owner goes away, and they haven't given it to anyone else themselves, then the book has no owner at all. And if something has no owner, then nobody can access it. It's useless, and that's when we can just free it. So this is basically how Rust does memory management, right? When you allocate a pointer, it has an owner, whoever allocated it. It gets given from place to place to place. And at some point, the last person who was owning it goes away, and we can free it automatically. In terms of aliasing and mutation, we're basically safe here because there's no aliasing, right? So we always want to be sure that we don't have both those things, or if we do, that we know why it's safe. In this case, there's no aliasing at all. The object moves just from person to person. And the next thing is something called a shared borrow, which is written &T. And with a shared borrow, the idea is that you can give out many copies of it. They're all references to the same piece of memory. But actually, let me take a step back. Before I explain the shared part of the borrow, let me explain the borrow part of the borrow. The idea of borrowing is, a lot of times in your code, you don't want to give ownership of something, of some memory, because you don't want to give it away completely. You just want to allow another function or whatever to use it for a little while. Just like if I give a book to you, I don't necessarily want you to take it home and throw it away when you're done with that. I'd rather you give it back to me. Like, it still belongs to me in the end, even if you're using it. That's what a reference is in Rust, and that's what a borrow is. And then a shared borrow means that I'm not lending it out to just one person, but to many, right? So, like in this picture, all of us are sharing a reference to the same book here, and we can all read it. The key part of this is that we can only read it. So we can't be making changes to it while it's shared out among many people. And eventually, the people we've shared it with are going to go away, and the book, at that point, it returns to its original owner, and it's no longer borrowed, right? It's just theirs again. So in terms of aliasing and mutation, we have aliasing here, because many people can access it, but we don't have mutation, because it's read-only. And the final thing is a mutable borrow. And this is another kind of borrow, so I'm not giving away ownership. I'm just giving away access to the memory for a little while. But in this case, it's mutable access. The memory can be changed by the person I've given it to. And what that means is, essentially, it's going to go it doesn't get passed to more than one. It can only go from one person at a time. So I can lend it to someone. They can lend it to somebody else. But it's always passing like a token, right? And eventually, it'll make its way back to the original owner. So here again we have mutation, but we don't have aliasing. So let's look at this, some real code now instead of just stick figures. And you'll see that these same ideas come out. So here's a function, an example function that creates a vector. And just like in C++, that vector is going to be stored on the stack. So it calls this function vec_new. New in C++ is a keyword, but in Rust it's just a function name. It creates a new vector and it returns a vector. Or it creates a new vector and returns it to the owner. And it gets stored on the stack, so we have the data and the length and the capacity inline. And then we're going to add some elements on, and those will go in the heap. So you see that the memory layout is exactly what I showed you before. And finally, we're going to call this function take. And take, the argument of take is a vector of ints. So it's saying, basically, when you call me, you have to give me ownership of some vector that I can use. So what happens then is we're just going to copy, at runtime, we're going to copy the fields over into take stack frame. And now it's been moved out. We'll see what this means in a second, but basically I've given it away. And we'll go over into take. And take can do whatever it wants to do. It owns this vector now. The key point is when take returns, it's going to free everything it owns, because everything it owns is no longer accessible to anybody else. So it frees the vector, and we come back here. Right? So everything went swimmingly in this example, but what I didn't show you is what happens if you try to misuse it. Right? So here I have a vector, I made it and I gave it away. But what would happen if, after I've given it away, I tried to keep using it anyway? That would be bad, of course, because that's been freed now by take. And the answer is that Rust is going to give you a compilation error, because Rust tracks what did you give away and what is still yours. In this case, you've moved vec into the take function, so we'll get a compilation error here. Right? And this prevents things like using after free and double moves and so forth. So let's look at borrows then. This is the other side. So we'll start out with a simple example, right? It's basically like the same thing we just saw. We're going to create a vector. Then we're going to call this function use. And unlike last time, use doesn't need to take ownership of the vector. It just wants to read some data out of it for a while. So it takes the argument type &vec, which you can read as kind of shared reference to a vector of integers. And on the other side, we also don't pass in the vector directly. We use the ampersand operator to take its address and make a reference and pass that in. And now, so at runtime, that means we're not going to copy all the fields. We're just going to make a pointer up into the stack and give it out. Use can do whatever it wants to do. And when it returns, we don't free the vector because it didn't own the vector. It just drops its pointer and everything goes back to normal. So those examples are kind of simplistic. I think they give the idea of ownership, but I wanted to show you a little bit of more realistic Rust code and also make use of a few features that you wouldn't have seen otherwise. So this is a function which takes two vectors, iterates down them, multiplies the corresponding elements, and then sums up the result. And the way it does it is it uses a for loop, which is basically the main way to iterate through things in Rust. You use for loops in combination with iterators, which you've probably heard of from other languages. So an iterator just walks through the elements in a collection one by one. And you can also combine iterators in various ways. So one of the things we can do is zip two iterators together. In this case, we're zipping the iterator of the vector 1 and the iterator of the vector 2. And that gives us an iterator that will walk down pairs, basically. The 0th elements, then the 1th elements, 2th elements, and so forth. And then, within the for loop, we can multiply those corresponding elements. And you see here that I don't actually write elem1 times elem2, but rather I have to first dereference it. The reason is, as we iterate through a vector, we're not getting the values and copying them out. We're getting pointers into the vector. In this case, that's a pointer to an integer. But if this were a vector of strings or of something bigger, that would be very useful. And then finally, we can return this result, right, which we're accumulating into a local variable. So now I wrote this code with shared references, meaning &vecs, because all it needs to do is read those vectors. And because it's a shared reference, that means we can reuse it in more flexible ways. So we might have a function like sum of squares that just takes one vector and passes the same reference to for both arguments. So in that case, we're squaring all the elements in the vector and adding them together. And that's perfectly safe because we can have multiple shared references to the same memory. There's no problem. And again, the reason that there's no problem is because shared references won't permit mutation. Right? So if we had a shared reference like here, and we tried to call push, or we tried to mutate one of the elements in the vector, we would get compilation errors. And it would basically say, you can't mutate through a shared reference. That's a little bit of a simplification. There are ways to designate special data and say, this is actually mutable even when it's shared. That implies some restrictions. I'm not going to go into it here, but for the most part, this is the pattern that you follow in Rust. That you have shared references, they imply immutability. So let's look at mutable references. Here's a function that takes all the elements from one vector and pushes them onto another one. Okay? And it works using so it takes as argument a mutable reference to the vector it wants to push onto, as well as an immutable shared reference to the one it's going to read from. And then it iterates over the from vector using a for loop and calls push. And it can do that because it's calling push on a mutable reference, so that's perfectly legal. And if we kind of walk through what happens here, we're going to start, we have a from and a to, and they're both pointers to somewhere. I didn't bother to draw out all the details, but somewhere up the stack there are some vectors, and we're pointing at them. And then we're going to iterate through. So we're going to create an element, and we're going to move it along as we iterate. And for each element, we're going to read out the value, push it onto the 2 vector, and then move to the next one, right? This is just like in C++, basically. When you iterate, we just grab the start and the end point, and then we bump the pointer along. So it's very efficient, one of those zero-cost abstractions I was talking about. And we'll do this for each element. So you may have noticed I made a kind of implicit assumption when I was explaining what would happen. I was assuming there were 2 vectors, and that from and to were different bits of memory. If we don't make that assumption, if we say that maybe from and to are in fact the same vector, as might be true in C++ or some other language, then we could run into trouble, right? Because now we've got this pointer right into the from vector. We're going to push it on to the 2 vector. That might require reallocating the 2 vector, which is also the from vector. And that would copy the memory out and free the old memory. And now our pointer is just pointing out in the middle of nowhere. And as we bump it along, we're still walking through the old pointers, old data. And that's called, that's a dangling pointer, but more generally, this is iterator invalidation. That's what they call it in C++. And actually, this is a problem in garbage-collected languages, too. So if you run in Java, for example, you won't get a crash, but you do get undefined behavior. You get an exception. They try to throw an exception, but it's not guaranteed. So this is another of those problems that GC doesn't actually solve in a deep way. So what happens in Rust? Well, let's say we have this push-all function that you just saw, and I try to call it with the same vector. It turns out that's not actually possible, because to do it, I'd have to make a shared reference, and I'd have to make a mutable reference. Right? So I first make, let's say, a shared reference here, and then I make a mutable reference to the same data, but that's an error, because the compiler won't let you share data and take a mutable reference to it at the same time. So essentially, we guarantee you that whenever you have a mutable reference, you in fact have the only way to access the memory that it's pointing at. And that's really useful for reasoning about, it's really useful for proving safety, but it also turns out to be, I think, how people generally think about things. So while you're mutating something, you're just thinking about the thing that you're changing. You're not thinking about indirect effects that it could have on all other kinds of data. And we preserve that invariant for you. But I only talked about half the story here, because I showed you how you can't make 2 references to the same memory. But there's another way you could have aliases. If you think back, all the way back to the first example I gave of bad C++ code, I had a vector. This is the Rust equivalent. I had a vector, I took an address of one of its elements, and then I pushed onto the vector, right? And here we still have aliasing, but we've only made 1 reference. We just have aliasing from the reference and from the original thing that we made a reference to. That's a little bit different, but it turns out it's also illegal, of course. And, well, I guess I'll step through this. This is what goes wrong. We push onto the vector, we free the old memory, and we're left with the dangling pointer. And the reason that's illegal is that there's a rule in Rust which says while something is borrowed, you can't change it. So in this case, we borrowed vec of 0, and we made a reference to it. That means we can't be pushing onto the vector until that reference goes away. So that's the basic, that about sums up the basic ideas of the Rust type system. But there's one thing I want to dive into a little more detail about, because I kind of hand-waved my way over it. So I talked a lot about time. If you notice, I just said something like, while something is borrowed, it can't be mutated. And before that, I said, you can't have a shared and immutable reference at the same time. But I didn't really say what I meant by time. So I don't mean that there's like a stopwatch running and somebody's checking and seeing how long it lasts. I mean something a little more abstract that we call lifetimes. And they refer to, essentially, the time in which some code is executing. So here I have a little function which creates a vector, iterates from 0 to the length, and takes the address of each thing in turn and does some pushing. And if we look at this, from the compiler's point of view, there are a lot of lifetimes here. Right? There's one lifetime which corresponds to the entire function. So the time in which this function is executing, from the moment it gets called to the moment it returns, that's one lifetime. And then within that, there are some sub-lifetimes, like the time it spends executing or creating the vector, calling vec new, the time it spends in this loop, and the time within that loop for each statement in the loop, and so on. And we use these lifetimes to think about when 2 things are occurring, possibly simultaneously, essentially. So part of every reference, when you make it, there's an associated lifetime saying how long it's good for, and it can't be used outside of that lifetime. Right? So that's basically how we define what's at the same time. So let me display the example a little more detail, right? In this particular function, here we're borrowing the ith element of the vector, and that element pointer is only going to be used within the loop. So that means that the lifetime of that element pointer can be confined to this loop. So we say, basically, outside of that loop, the element pointer is not valid anymore. And that means that the restrictions that we put, the restrictions that occur because the element pointer exists, they only apply during the loop. So if the vector is borrowed here, then it's not legal to push it inside the loop, but it is legal out here because there are no references anymore. The lifetime expired, the memory is yours again, and it's not aliased. So this same mechanism actually solves another problem that occurs sometimes in C++. It's kind of a subtle, yet another variation on memory safety. There are a lot, which is basically returning pointers into your stack up to one of your callers. So if you, in this little bit of code, I have a vector, I take the address, and then I try to return that out. And the problem is the vector is going to get freed as soon as I return, and now the pointer I gave isn't valid anymore. In Rust, this will be an error, because what will happen is it'll say, you're borrowing from the vector, and the vector is going to get freed as we exit the function. So that's the maximum lifetime that I can permit this reference to have. Anything longer than that can't be safe. And then here, when you try to return it, well, that would only be valid if the lifetime extended past this function, because you're giving it out to the caller. So the lifetime would have to encompass the caller too. And that can't happen. So you'll get an error there as well. So the next, that really is the type system now, I think. That's the core bit. But we can actually go a lot further. So if it's not that only thing you can code with in Rust is strict ownership and shared references and mutable references. What we also allow you to do is to build up abstractions, right? And this gets back to that zero-cost abstraction that I was talking about. So we have a lot of libraries in Rust that add a lot of new kinds of things. I mean, everything from containers, like I've been talking about, vectors and hash maps and so forth, but also different memory management strategies, like reference-counted pointers, where you can only access the data, you can basically be sure that you can only access the data when the reference count is greater than 1, and it will get freed automatically when reference count drops to 0, and that sort of thing, as well as parallelism abstractions. And all of this is made safe by using this ownership and borrowing techniques. Right? So that's how we guarantee that you're using the API correctly and you can't be abusing it. I'm going to dig into this a little bit in the context of parallelism. So I want to go through some of our parallel libraries and show you how they work and how they employ the same mechanisms we already presented. So, but before I do that, let me take a step back and just briefly explain what a data race is. Because I kind of covered it a little bit in the introduction, but it was a little fast. Maybe some of you aren't as familiar with that. So what happens, the reason that parallelism is kind of scary, basically, boils down to data races and the possibility that you have two threads with access to the same memory that are both trying to change it, right? And it's particularly scary because that works most of the time. So what happens is one thread comes along, and it goes and makes some changes to the memory, and everything's fine. And then another thread comes along, and it happens to be later, and it makes some changes to the memory, and everything's still fine. But once in a while, particularly when your customer or a boss or something is looking at it, or maybe just Tinderbox, I don't know, once in a while, but never on your machine, both of those threads come together at the same time and decide now is a good time to write to that memory, right? And when that happens, like, everything breaks down. And you get undefined behavior, or crashes, or worse. So we want to avoid that. And if you think about it, there are really three things that have to come together to make a data race happen. You have to have aliasing. That's how you get two threads with the same data. You have to have mutation, because if they're just reading it, it doesn't matter. And they have to not be ordered, right? And it sounds sort of unlikely, all these three things happening at once, but they're all really common things. So in fact, they happen all the time. And it's not that hard to do. It also might sound a little bit familiar, right? I've been kind of talking a lot about aliasing and mutation as the source of memory safety problems. They're also the source of data races. So all the tools and the language mechanisms I've been talking about apply pretty well towards preventing data races. So I'm going to cover three patterns that are kind of the analog of the three patterns: ownership, shared references, and mutable references. I'm going to cover those, what's their parallel equivalent. And so for ownership, I was giving vectors between function calls, But in parallel, you can use the same idea of ownership to talk about transferring data between threads. So I can have one thread, and he sends a message over to another one, and maybe that thread creates another message and replies with it. And at all times, we're just transferring ownership back and forth. No, we're never sharing that data. This is what it looks like if you write some Rust code. You start out by making a channel. That's just like a Unix pipe. You get back two endpoints, transmit or send and a receive. And then basically what you put into the transmit end will come out on the receive end, right? It's a way to communicate. And when you start out, they're both owned by the same thread. That's not so useful. You can send messages to yourself. But then what you do then is you can like spawn off another thread here, right? And that's with the spawn function. And the spawn takes as argument a procedure, which is proc. A procedure is essentially a closure which takes ownership of all the things that it references. So in this case, the procedure, which is going to become the new thread, references the TX endpoint, the transmit endpoint, and takes ownership of that. So that means it's going to move over into the new thread. And that means that the original thread no longer has access to it. Now we've spread the endpoints across two threads. So when the second thread, the child thread, is executing, it can create a message, which I'll make as a vector just for fun, and then send the message. And when it does that, basically, the fields of the vector, the fields of the message, are copied into the transmit pipe. And then at some point later, the other thread will come along and receive it, and it'll copy those fields over to itself. And you're done. Now we've transferred the vector. It never belonged to two people at once. It just moved from place to place. And the interesting thing is that we didn't copy the data of the vector, right? We just copied those three fields. That's like 12 bytes of memory or whatever. That's nothing. If this vector were 10 megabytes, it would cost the same as if it was 100 megabytes or 5 megabytes. So it's a very cheap operation, which is very good. But even though it's a very cheap operation, even though we are preserving safety completely, right? And then the next thing we might want to have is shared read-only access. So we might have two threads. They might share like a common hash map or something, or a common vector, and try to make use of it. And the way we do that is with a type called arc, which stands for atomic reference count, not automatic, if you're familiar with that. And what arc basically does is it has embedded within it the data that should be shared. Right? So in this case, it's going to embed a vector. And you notice this is laid out inline, like the zero-cost abstraction I was talking about. There's no extra objects involved. And in particular, it's owned. So the arc owns the thing that it contains. That means the arc knows that nobody can get access to that vector without going through the arc in the first place. So then in order to make it safe, basically the arc acts as a smart pointer. If you know C++, still that term will be familiar, but what it means is you can dereference the arc and get back a pointer to its contents. And the only kind of pointer you can get is a shared reference. So the only thing you can do with an arc is get an immutable access to the data it owns. So that data can't be changed by anybody, though many people may have access to it. And similarly, you can have locked access, right? Where I want to allow writes, but they're going to take turns. So the left thread might execute, and while it's doing its writes, the right thread has to wait before it can go. And thus we avoid data races. We can do that too. And we use a pretty similar mechanism. So this is a little bit of code that will acquire a lock, increment an integer, and then release the lock. And to do it, it starts out by taking a pointer to a mutex. And then that pointer itself, there's nothing you can do with a mutex. You can't get access to the data that's inside there unless you call mutex.lock, which will acquire the lock and return to you another object, which is called the data. And basically the destructor of that object, what happens when it goes out of scope, that's going to release the lock. So until this goes out of scope, the lock is held. And moreover, if you want to access the data, you have to go through that object. So that guarantees that the destructor hasn't run yet. So you can't release the lock too soon either. As long as you're accessing the data, you are going to be holding the lock. And finally here, when we exit from this function, we will just release the lock and close the destructor. So those are three pretty simple parallel APIs. And I think this is something we are actively working on, or planning to actively work on, maybe I should say, and extend this set to cover a lot more interesting and complicated abstractions. Some of them we already have, especially for our own internal use. So for example, atomic primitives and non-blocking queues, I think there may be some concurrent hash tables floating around. Is that true? No. Okay. Not yet, but maybe in the standard library. Or yes, there are some concurrent hash tables, lightweight thread pools, and so on. And I think we can go further. Come talk to me about it later if that excites you. But basically, the bottom line is we have all these different ways. We can implement many safe patterns for parallelism, but for all of them, we can guarantee data race freedom. So whichever one is most suitable to your task, you can use it, but you won't have to worry about data races and crazy irreproducible bugs, right? And now, in the interest of full disclosure, I want to come to one last part of the talk. I've been talking about safety pretty much this entire time, but there's also a little bit of unsafety in Rust. And so essentially when you want to talk about, there are lots of things that one might want to do when writing up efficient implementations of, say, a concurrent hash table or something like that our type system can't prove to be safe. We can't understand. They're not covered by the safe. Basically, there are safe patterns that we haven't put in the type system. That's what it boils down to. And we want to let you write that kind of code too. And sometimes you have to. So examples might be working with uninitialized memory, or interfacing with C code, because all C code can do whatever the heck it wants, right? And maybe building parallel abstractions, like I mentioned. So in those kind of things, what you can do is you can write an unsafe keyword. And basically, you're telling the compiler, hey, trust me, I got this. This is, I know what's going on here. It's not obvious to you, but it's correct. And the idea of this is not that you go, every time the compiler is irritating you, you put unsafe in your code and just turn it off. Rather, the idea is that you write a safe wrapper around it. That is to say, some other function or a class or something which will validate inputs such that no matter what the outside world does to that function, it won't crash and it won't cause a data race and all those things. And then inside there, you wrap it up and you get to break the rules. Now, every language has this. They may not use a keyword for it. They might just call it an FFI. But every language has a way to drop the safety guarantees, to drop the language rules, and break down and call assembly code. But what we've done is moved it into Rust as a first-class thing because it's useful, but also because it means we can do things like write all of the Rust libraries in Rust. There's almost virtually no C code whatsoever in the Rust standard library. I think a couple of glue functions here and there. And that's only possible because at some point you have to drop the veils and just write some assembly code. That's what it comes down to. So the status of Rust, I would summarize it as rapidly stabilizing. We are working towards a 1.0 release this year, which is going to mean that we have a stable syntax that will finally stop changing. That will stop changing. We have a kind of stable core type system that describes most of what we want to do, and where we have some planned extensions that we're going to add into that are future compatible. And we'll have a minimal set of core libraries. And once that's done, we're going to rapidly iterate, grow the libraries, finish off the remaining work, and I don't know, and then we'll see what the future holds. But that's our plan. So in conclusion, Rust is a language with the goal of letting you have control over what you're doing, but without compromising safety. Right? So we want to enable zero-cost abstractions that are safe. We want to have a type system that lets you describe and make sure that they're safe, and do all this.
In your vector example, is the actual elements?
The question was, in your vector example, are the actual elements heap allocated? Yeah. You mean like yes.
So
the element array is heap allocated. Yeah.
How is that, how do you tie the ownership of that to the vector container?
The vector container,
How does the compiler know that you take a reference into the element array?
the way it knows it is, so it's a little bit tricky with vectors because they're actually a library type. But what it comes down to is that in order to get an index into the vector, you end up supplying a reference to the vector itself, so a borrowed reference to the vector itself. And then you can deduce that if you've borrowed the outer container, you can borrow things that outer container owns as well. So once you have a borrowed reference to one thing, you can make a borrowed reference to anything that is followed like a transitive ownership chain. Does that make sense?
Well, so how does it know the ownership? Like, what happens if I write my own library class where some things it is safe to give out points to even
Yeah, it knows because when you make it, if you have something that's heap allocated, I didn't show it, but there's a type called box, which is basically a boxed something in the heap that I own, and boxes move from place to place. And so if you internally to the vector, there might be, for example, a boxed array. And so the actual vector is implemented somewhat differently, but that would be one way to do it in your own code. So. Well, I think probably the biggest pain point has been the fact that we've been changing the language and improving it, and essentially that requires them to keep up with us. But the type system itself, from my understanding, has scaled pretty well. Patrick may have some comments, but
yeah, we've hit a lot of the issues have been bugs. A lot of the issues have been bugs in the implementation. The overall discipline, I think, has not been too difficult to follow. I mean, there's most of the issues we get are issues in
yeah.
The precise way that the borrow checker checks all these invariants, reasons about the time or reasons about lifetime and whatnot. Those are most of the issues that we hit. They're fixable, and we continue to improve them all the time. So those, I don't speak for the entire team, obviously, but I feel that the discipline, the kind of overall type system strategy that Rust enforces has been pretty practical.
So, summary, pretty good.
We still have a lot of unsafe code, but a lot of that's unavoidable. We're on C libraries, and also we're doing things like we have Rust objects which are managed by the SpiderMonkey garbage collector,
right.
which is really cool that you can do that, but the interface there has to be written in dialect, obviously.
So, yeah, I think Servo does, the intention of unsafe is certainly not that it only ever gets used by the standard library. I mean, we include it because we expect end users to do nifty things like tie in with the SpiderMonkey garbage collector that we haven't envisioned. I think that's a good thing.
But whenever we use unsafe, we use it to build safe abstractions.
Yeah.
So we don't use it, we don't expect, we expect the amount of unsafe codes to remain relatively constant as we build more and more and more, features into Servo, which is the important thing. You don't want new features to compromise the security of your browser engine, and I think Rust has done a pretty good job of enforcing that.
Anything on IRC or anything?
There is nothing on IRC that I can see.
All right. Thanks, everybody.